Hello and welcome aboard Rittenhouse Air. Today, our flight will be exploring our solar system. The first stop on our trip is the Sun. We now ask that you place your tray tables in the upright and locked positions as we prepare for takeoff. This is our Sun. It's a nearly perfect sphere. The Sun has a diameter of over 850,000 miles. The Sun is actually so large that more than 1 million Earths can actually fit inside of it. But the Sun is not as big as some other stars. Our Sun is actually a medium-sized star. In comparison to Betelgeuse, we can see how much smaller it is. The Sun is powered through a process called nuclear fusion. In this process, two particles of hydrogen combine through heat and collision to form a new particle of helium. This interaction produces light, heat, and energy that sustains us on the planet Earth. On Earth, the Sun's color can appear to change over time. This effect is due to our atmosphere and how it refracts light. As the white light from the Sun collides with nitrogen in the atmosphere, the nitrogen will scatter blue light more easily than other colors. As the collision and scattering continue, it spreads the blue color across the sky. This is why the sky is blue. As the Sun sets, its light must travel through more atmosphere, collide with more atoms of nitrogen, producing redder colors. Now let's take a look inside. There are 6 layers of the Sun: the core, the radiative layer, the convective layer, the photosphere, the chromosphere, and the corona. First, let's look at the core. It's an extremely dense object. It contains 50% of the mass, but only 1.5% of volume. The pressure at the core is 250 times greater than on the Earth's surface. The core must endure the pressure from the layers above, pushing down on it, prevent itself from imploding from its own weight, and contain the pressure from the nuclear reactions going on inside of it. The nuclear reactions inside the core produce intense gamma rays that collide together to form X-rays. As the X-rays travel upwards, they enter into the radiative layer. This layer extends from the core to a distance of 70% of the way to the Sun's surface. This layer is filled with atoms of hydrogen, helium, and free electrons floating about. The free electrons, which are not attached to the atoms, collide and bind themselves to atoms of hydrogen and helium, causing them to be ionized. The collision of the atoms and free electrons happens so often that it may take a single particle 1 million years to get from the core to the convection layer above it. Before we move on to the convection layer, there is a thin layer called the interface layer. This layer is where the Sun's magnetic field is created. The field is most likely created from the flow of charged ionized particles flowing in a shearing motion. Next, we enter the convection layer. This layer is cooler, around 3.6 million degrees Fahrenheit. Photons and electrons from heavier ionized particles, such as oxygen, iron, and calcium, find it easier to bind and stay attached to their parent particles. As a result of this, these ionized particles can block more radiation coming from the layers below. This imbalance of forces causes the particles to rise to the top of the boundary between the convection layer and the photosphere, where they cool and transfer energy, heat, and light to the Sun's surface. Evidence of the convection layer currents can be seen on the surface as cell-like structures called granules. The gases come up in the bright areas and sink back down in the dark areas. At the surface of the Sun, or the photosphere, the gases can radiate their light and heat into space. Since the Sun does not have a solid surface, it produces some interesting effects. On solid spherical surfaces, the time it takes to complete a rotation is the same everywhere. This is not true on the surface of the Sun. On average, the Sun completes one rotation in about 27 days, but at the poles it takes longer, around 30 days, and faster at the equator, around 24 days. The photosphere is the region that sunspots appear. Sunspots are the cooler dark spots seen on the surface of the Sun. While they may look black, they're actually a cherry red color. Their temperature hovers around 6,000 degrees Fahrenheit, while the surrounding area is around 10,000 degrees Fahrenheit. Sunspots are thought to be caused by disruptions in the Sun's magnetic fields. As ionized particles interact with these disruptions, that area is cooled due to the decreasing supply of heated particles from the convection currents. These spots can be quite large sometimes, as large as the planet Earth itself. Sunspots go through an 11-year cycle, where the number of sunspots increases and then decreases. This cycle also correlates with the level of other solar activity as well. Just above the photosphere, we run into a thin layer of atmosphere called the chromosphere. This layer is extremely hot and very active. The temperature here ranged from 10,000 degrees Fahrenheit to 36,000 degrees Fahrenheit. At these temperatures, hydrogen gives off a red color, but most of this light is blocked by the larger and brighter areas around it. Often, the sun will shoot off massive amounts of gas and plasma in eruptions such as prominences, coronal loops, streamers, and flares. These mini eruptions are charged ions and often flow along the magnetic field lines of the sun. The largest of these are the CMEs, or the coronal mass ejections. These ejections escape the magnetic field and gravity of the sun and fly into space. Because of their immense size, electrical charge, and heat, CMEs are a serious danger to our satellites, astronauts, and our electric grid. From here, we go to the outermost layer of the sun called the corona. The gases in this area are superheated to 1.8 million Fahrenheit. At these temperatures, particles of hydrogen and helium completely lose all of their electrons, causing them to become highly ionized. The cause of the superheating in this region is still unknown, but it may have some correlation to the interactions along the magnetic field. The gases of the corona go out into space for millions of miles. Because the gases are superheated in this region, gravity cannot contain them and they escape. The solar winds are the most common of these set of eruptions. They travel out from all directions and into space. Traveling at 1,000,000 miles an hour, they eventually collide with planet Earth, causing the auroras. Scientists are actively studying the sun today, since it affects us so much. Check out some of these great missions NASA and the ESA are currently working on. This concludes our first stop, and thank you for choosing Rittenhouse Air. Next stop, Mercury.
Liquid water has been found on Mars.
This was perhaps the year's biggest single story in our ongoing journey to Mars, but it's certainly not the only one. Managers from
During its short 2-hour flight in February, Europe's Intermediate Experimental Vehicle validated critical re-entry technologies and proved Europe's ability to guide its own vehicles back to Earth safely.